Okay, so our second speaker of the day is Nathanael Cox, who will be speaking to us about effective algorithms for computing quotients of semi-algebraic equivalence relations.
Thank you for that introduction. I want to thank all of the organizers for putting on this series of talks. And so, as he said, I am going to talk about an effective algorithm for computing quotients of semi-algebraic equivalence relations. Right? Okay, there we go. Okay, so first, I'm going to briefly talk about kind of just quotients in general. So, as we all kind of know, talking about taking quotients of topological spaces just in general is kind of a natural and practical thing to do. We do it all the time. So for example, you can obtain the real projective plane by taking an equivalence relation on the unit circle and then quotienting out by that equivalence relation. And another kind of quotient space that's kind of near and dear to me and some like the work that I've been doing with my advisor is this notion of a Reb space. So if X is just a topological space and F from X to Y is a continuous function, Y also is a topological space, but I forgot to mention that. So we can define an equivalence relation where if you have two elements of X, they're equivalent if and only if they map to the same point in Y, and they're in the same fiber of the point that they map to, so the same connected component of F inverse of Y. Then that quotient space on X by that equivalence relation is called the Reb space of F and is denoted Reb of F. And then it's a little bit more commonly referred to in the case where Y is the real numbers. And in that case, we call it the Reb graph of F. However, so quotienting is a nice thing and comes up very often. However, it doesn't always preserve nice properties of our original topological space that we might like. So for example, a quotient space of a Hausdorff space may not always be Hausdorff. And similarly for simply connected spaces, contractible spaces, and locally compact spaces. So one way that's kind of been thought up to deal with this is try to restrict our set of topological spaces to a more tame set in the hopes that we might preserve more properties under quotienting, right? And so the particular restriction that I'm going to be focusing on is called an O-minimal structure. And if you don't know exactly what those are, think semi-algebraic sets, which are sets that are defined by polynomial equalities and inequalities. And we refer to them as tame just because they have a lot more like nice properties that are easier to deal with in addition to like preserving things under quotienting. So they only have finitely many connected components. In this kind of restriction, the functions only have finitely many discontinuities and stuff like that, right? And so kind of the big theorem that we're doing our work off of is due to Van den Dries, I think in the early 90s. So if you take E as a subset of the product space of X with itself to be a definably proper equivalence relation on a definable set X, where an equivalence relation is proper if the projections onto each component, so the projection from E into X is a proper map in the traditional sense, then the quotient X mod E exists as a definably proper quotient of X. And so the X mod E is homeomorphic to some definable set Y. And again, if you're not as familiar with definability, you can replace it all with semi-algebraic sets. Definable is just a slightly more generalized concept. Right? Okay. And so kind of being able to apply that theorem, so the circle is a semi-algebraic set. And so you can show that that equivalence relation that generates the real projective plane is semi-algebraically proper, and hence a real projective space is homeomorphic to a semi-algebraic set. Maybe slightly more substantively, we were able to show in a previous paper that if X is definable, then the Rev space equivalence relation is definably proper, and hence this definability is preserved when passing to the Rev space as well. And so kind of the work that we did on this project was to create an effective algorithm which takes a description of a semi-algebraic set X and a description of a proper semi-algebraic equivalence relation E on X and returns a semi-algebraic set Y, which is homeomorphic to the quotient space, and a semi-algebraic function kind of acting as the quotient map, right? And so the inputs and outputs of our formula are, so we want to input P1 and P2 are two sets of polynomials, and phi X and phi E are both our P1 and P2 formulas respectively, right? And what that means is, so a formula is kind of a Boolean formula whose atoms are polynomials, are polynomial equalities and inequalities. And then it's a P formula if those polynomials all come from a set P. So phi X represents a formula made up of polynomials from P1, and phi E is a formula made up of polynomials from P2. And so in the realization of these formulas, so the set of elements that make the formula true form a semi-algebraic set, right? And then the output is also very similar, two different sets of polynomials and a formula whose phi F, whose realization is the graph of our function F, and then phi Y, whose realization is the semi-algebraic set Y. Right? And so one thing that is always important with these kinds of algorithmic problems is how complex is it in terms of the input variables, right? And so the complexity here represents the number of arithmetic operations performed by the algorithm on the inputs to obtain the outputs. And so kind of what an arithmetic operation is depends on what field you're in. So if you're looking under, or not just even field, you can look at it under rings as well. But so if you're in a field, you have all the operations of a field. If you're in a more general ring, you might not have, you might not be able to divide. And so then you might have to do more operations in that case. And so for us, this is all kind of will be measured in terms of the number of input polynomials, their degree bound, and then the number of variables. So if you're in like R2 or R3. Okay. Right. So some of the algorithmic tools that we use in this kind of field of algorithmic semi-algebraic geometry, there's quantifier elimination, semi-algebraic triangulation, and you're able to compute semi-algebraic descriptions of connected components. So for my algorithm, we mostly focus on quantifier elimination and semi-algebraic triangulation. So I'll explain those in a little bit more detail here. So quantifier elimination, so you have a set of polynomials where there are at most k polynomials with the degrees bounded by little d in m plus n variables with coefficients in R. So in general, R is a real closed field. You can generally think of it as just the real numbers. And if you can partition the first m variables into blocks that represent quantifiers. So the quantifiers for our formulas are there exists and for all. If you have a formula phi of y that has quantifiers, then you can generate an equivalent quantifier-free formula C of y. And so by equivalent, we mean that their realizations, the set of solutions are the same. It's just one formula has quantifiers and one does not. And more importantly, there's an algorithm that lets you compute this quantifier-free formula that has the following complexity. And so kind of the thing to note is that this algorithm has complexity that is singly exponential in terms of the size of the set of input polynomials, right? And I don't know, if you do a lot of other like algorithms in slightly more efficient fields, this might seem like kind of a pretty bad complexity, but in algorithmic semi-algebraic geometry, this is kind of the standard to like about what you'd expect. And in fact, this semi-algebraic triangulation is actually worse. So the kind of the theorem for triangulation is if you have a closed and bounded semi-algebraic set with some finite number of semi-algebraic subsets, you can obtain a simplicial complex and a homeomorphism such that each of those subsets is the union of images by H of the open simplices of K. And in fact, you can choose the vertices of your simplex with rational coordinates. And if you have a set of polynomials describing your semi-algebraic set S and the subsets, then you can compute the triangulation in the following complexity. And so as you can see, this complexity is actually doubly exponential in terms of the size of input polynomials, so quite a bit worse than the quantifier elimination case. And it's kind of a big open problem in algorithmic semi-algebraic geometry of how does one compute semi-algebraic triangulation in singly exponential bound. And so we're not necessarily even sure if it can be done.
Nathanael, can I ask a quick question?
Yes.
If you go back to the slide on quantifier elimination, what happens to the size of the polynomials under the quantifier elimination procedure? Is that where the complexity comes from, or?
Correct, yeah. In general, for most of these algorithms, the size of the set of output polynomials is of the same order as the complexity of the algorithm.
Thank you.
And so that would be kind of the same thing you would expect here. Right. And so our result is, again, making effective that result due to Van Indries that says that if you have a definably proper equivalence relation on a definable set, then the quotient will exist as a definably proper quotient, right? But to be able to do like this algorithmic stuff, you need to have semi-algebraic sets. So that's what we restrict ourselves to. So you have two sets of polynomials, P1 and P2, with the first one containing K1 polynomials and the second K2, and their degrees are bounded by D1 and D2 respectively. Then if you have a formula, a P1 formula phi x and a P2 formula phi e, that again represent a semi-algebraic set and the semi-algebraic equivalence relation on that, then there exists an algorithm which returns formulas whose realizations are semi-algebraic sets Y, that's homeomorphic to X mod E, and gamma of F, which is the graph of a semi-algebraic function F from X to Y. All right, and then moreover, if K1 and K2 are approximately equal and D1 and D2 are approximately equal, we can get an upper bound on the complexity of the formulas here, where K and D kind of represent the approximately equal value of K1, K2, and D1, D2 respectively. And so as you can see, this is also doubly exponential in terms of the input variables, which, as I mentioned, we use semi-algebraic triangulation in the algorithm, so we shouldn't expect necessarily anything better than doubly exponential in such a general case. Right. And so kind of some motivation or maybe applications, quantifier elimination you can view it as a quotient. So while there are more efficient ways to do quantifier elimination, this algorithm could do it. And currently, there's not a better way to find, there's not a better way to calculate the Reb space of a semi-algebraic set. So this would be a nice way to find that if you really need the semi-algebraic description of your Reb spaces. And then there exists some other algorithms that do this, but none that find quotients, but none in like this level of generality. Right, so kind of an overview of the algorithm. So our algorithm mostly consists of making effective the steps that were in Van den Dries's proof, and we use the various effective tools of quantifier elimination and semi-algebraic triangulation that I had mentioned before. So we first we determine the dimension of our space X, which is represented again by phi of X, and so there exist algorithms that allow you to do this. Right, and then if D is bigger than 0, you can use triangulation and quantifier elimination to obtain a subset x prime of X that is of a lower dimension. And then you, so Van den Dries's proof uses induction. So at this point, we have to call the main algorithm again, but with our formula for x prime as the input. And then we just repeat this until we obtain a space that is dimension capital D equal to 0. Right? And sometimes you could go down one dimension, sometimes you could go down several. So it's hard to say exactly how many times you'll call the algorithm, but it could be up to D times. Right? And then when D equals 0, we can return a space Y prime that contains exactly the least element of each equivalence class and a map F prime that sends elements of X to the lowest element equivalent to it. And to do this step, we need quantifier elimination, right? And so from here, what we kind of have is we have a chain of subsets that are of lower and lower dimension, and then on the lowest dimension, we have a map to a quotient space. And then from there, now we need to kind of go back up the chain, and for each of the spaces of various dimension, we need to obtain the quotient map. And so the notation is going to get kind of complicated, but bear with it. So for each dimension delta that has a space associated with it, you can set your quotient space on kind of the higher dimensional space as y equals, so this notation right here, where this is the disjoint union of these two sets glued together on the map f double prime minus restricted, so f prime restricted to the set C of S delta intersect x prime. So basically it's the equivalence relation that's generated by x is equivalent to f of x, or in this case, x is equivalent to f double prime of x. So that's what this is. Right? And then from here, you can, with some triangulation and quantifier elimination, you can obtain this map P, where if there's not a function subscript, it's just a standard disjoint union. And so this one's kind of like gluing the disjoint union along like the function, right? And so the closure of all the delta dimensional sets of your triangulation, disjoint union with the lower dimensional quotient space that you obtain kind of on the previous iteration, right? And then the only problem with this map P is it doesn't quite have the right domain. We would like our map to be from X to Y. And so you get this, this commutative diagram, and where, again, sigma right here. So you can set F equal to G composed with sigma, where G is here, which I'll get to in a second. Sigma from X into S is the map that sends each element of X to the lowest element in X that's equivalent to it. So similar to what we do in the D equals 0 case. And then this C of S is the closure of this S that contains one element from each equivalence class. H is basically just the inclusion map on each component of this. And then here, J from X prime to Y prime is just F prime, and then on the C of S delta is just the identity map, and then we have this P from that we obtained through triangulation and elimination. That's kind of like almost our quotient map, and then we choose G such that this diagram commutes, and then if we compose G with sigma, we get a map from X into Y. That is the desired map that we would like. Okay, so here are my references. Are there any questions?
Thank you so much, everybody. Please unmute yourself and applaud for our speaker. So, as the slide asks, are there any questions for Nathanael? So maybe while people are thinking, I'm going to get the ball rolling with a question. So can you, or are you aware of, or can you imagine any settings in the applications of Reeb graphs or O-minimal structures in which the actual characterization of it, let's say for semi-algebraic sets, the actual semi-algebraic description of it is necessary?
So we haven't, I guess we'll say we haven't gotten quite that far into like exploring this to where the semi-algebraic description would be necessary. But I know like Reeb graphs and Reeb spaces in particular have like numerous applications in like computer graphics and medical imaging and data analysis and stuff like that. And so if, I don't know, if for some reason you wanted to kind of have a description of it, it could potentially be useful in those, in the scenarios where Reeb spaces are useful.
And thank you for the answer. It's a pretty tough question. So it seems like in this area there's a lot of single and doubly exponential bounds. Mm. Is your intuition, or is the intuition in general, that this is a general phenomenon, or do you expect if a space is sufficiently simple, I'm not exactly sure what's the equivalent of bounded geometry somehow, if there's some simplifying assumptions on the space, you can expect to do better than exponential computation time?
Yeah, so I know like you can put some restrictions on the triangulation and obtain some singly exponential bounds in that case, but like, I don't know, in general, it seems to be like, I guess if you want to do stuff like in generality, it seems to be singly exponential and doubly exponential is kind of what you should expect. And I don't know, I guess if you restrict it enough, you could probably like make it simpler than that. But even with some restrictions, you might still expect singly exponential bounds.
Thank you. I actually have more questions, but I'll leave off for a moment in case anyone else has anything they'd like to ask. Okay, so maybe I'll ask my question. I'll indulge myself. So is this procedure an all or nothing kind of procedure, in the sense that, let's suppose I have a characterization of a space and of an equivalence relation, and maybe I don't necessarily want like a semi-algebraic or O-minimal description of the whole quotient, maybe just a part of it. In other words, is there some way in which this procedure can be stopped or simplified and get some partial information, or is it really a sort of, you have to do everything together kind of deal?
I think like so the way I wrote the procedure, at least, it's kind of all or nothing. And the locations where you use the triangulation happen early enough that like even if you wanted to like start partially way through, like even if you wanted to stop halfway through, you would have already done the triangulation, and so that's kind of the computationally heavy portion.
Interesting. It's a challenging problem. Thanks for the answers. Are there any other questions for our speaker?